So we've seen that we can add a matrix, we can subtract matrices, and we can even multiply matrices. So another question is, well, can we divide by a matrix? Can we divide by a matrix? And really, division is really kind of what gives algebra its teeth, you know, because it allows us to invert equations to get solutions. So the answer to this is yes. It's a qualified yes. So in a sense, yes. Not all the time. So definition. We need a definition to start us off with what we're doing. So A is a matrix. In Mn, I'll use this to denote the square matrices. N by N square matrices. That's just shorthand. You know, why write N by N square matrices when I can just write M sub N every time. Then B is a left inverse of A, and C is a right inverse of A if BA is equal to the N by N identity, and AC is also equal to the identity. So the whole problem is, right, so the whole problem is we don't have commutativity, right? So with commutativity, we can show that for real numbers, a left inverse is a right inverse. We don't have that necessarily here at all, right? It'll turn out that they are equivalent, but we have to get there, right? It's not immediately obvious. So we have a theorem. If A is in Nn, has a left inverse and a right inverse, respectively B and C, then B is equal to C and A has a unique inverse. So proof of this fact. It's really kind of short, and it just uses associativity, right? It's a cute trick. So we've got B here. Well, B is equal to B times the identity. That's just true. But the identity, right? Well, we reverse this thing, and we get that this is B times AC. Well, the matrix product is associative, so I can switch this. This is BAC, which by definition of B being a left inverse, this is equal to IC, which is equal to C. Now, if B was any inverse, right, so if I have a right inverse and a left inverse, then I've got that B is equal to C. But let's say I had another right inverse, right? If I had another right inverse, this is also equal to C, so it's equal to B, right? So that means that everything is unique. If I had another left inverse, I have another left inverse, then I could go through this again, and I get a unique inverse. I get that all the inverses have to be equal, and so A has a unique inverse, and we're done. That's the end of that proof. Pretty short, but super useful, and it's a cute little trick using associativity and just the definition of the identity matrix. No, we want something a little stronger here, right? So one thing is that, well, we've got an inverse, right? But we have to know that there's a left inverse and a right inverse. But it turns out that we can just say that a matrix is invertible, right? So if this last theorem holds, right? So if the hypotheses hold, then we say that A is invertible. Which is great. And what's cool is we can actually tie this to our notion of rank as well, right? So theorem and our notion about existence of solutions, right, to AX equals B. This will have some very important consequences, right? So if an n by n matrix A is invertible, right? So it's got a left and a right inverse, and therefore they're equal, then it is non-singular. Moreover, if A inverse is the unique, inverse of A, then the solution to the unique solution to the equation AX is equal to B is simply X is equal to A inverse B. That's very nice, right? That's a very nice way to compute, right? So that means that if I have the inverse, then I can just matrix multiply the inverse by my B, and I get a solution immediately. That's really nice to have around. So if you can compute that, if it's invertible and you can compute it, then you can solve any of these equations. Anytime somebody gives you a B, you can always pump out an X. So clearly, right, if it's invertible, like clearly X equals A inverse B is a solution, right? And this is because A times A inverse B is equal to, remember, associativity. So an inverse is also a right inverse, so this is equal to IB, which is just equal to B. Right, so that means that A times this number was B, so that's a solution to that. But we need to know that it's a unique solution, right? So there is a solution, but it has to be unique. So suppose for the same B that AY is equal to B, then we've got that AX minus AY is equal to, well, both of these guys look like B. So this B minus B is equal to 0. Now we use the distributive law, and we get A times X minus Y is equal to 0. And now we're going to hit both of these sides with both sides of this equation, right? So this is just an algebraic equation. We have both sides with A inverse, so let's put A inverse here times 0 now. And what's going to happen to this guy? This guy will turn into the identity times X minus Y. Whenever I hit anything with 0, it just dies. So this is 0 again. And this is just going to be X minus Y is equal to 0, which is just X is equal to Y. Therefore, this is a solution, and it's a unique solution, and we're done. A is non-singular if there's an inverse. Well, we want to know if the converse is also true, right? So if we can move back on this and say that, well, if we have non-singularity, is this thing invertible? And the answer is yes. So that means that we have another equivalence, right? Well, we'll talk about that more when we set everything down. But so theorem an mn non-singular, then A is invertible. So if we combine this theorem and the last theorem, we get that A is non-singular if and only if A is invertible, which is really nice. Proof. Well, let's suppose xi is the solution to the equation ax is equal to 1i. So this is a column vector with a 1 in the ith entry, right? And suppose this is the case for I is equal to 1, 2, all the way up to n. Then let X be the matrix formed by all these xi's. So this is x1, x2 is the second column, all the way up to xn. And let's check it out. We've got A times X is equal to, well, when we multiply by a matrix, we can just essentially multiply all the columns. So this will just be AX1 in the first column, AX2 in the second column, all the way up to AXN in the final column. And by the way we've defined the xi, right, it's the unique solution to this, and we get, this is the vector with an entry of 1 in the first entry and a 0 in all other entries. Then we've got the vector with a 1 in the second entry and 0 everywhere else, all the way up to 1n. Well, if you'll notice what this is just the identity matrix. Therefore, X is a right inverse of A. So we have a right inverse, and now we need a left inverse in order to ensure that's invertible by our definition. Well, by our last video, there is a set of elementary matrices E1 up to EK such that if we set E equal to EK times all the way up to E1, then EA is equal to the reduced row echelon form of A. However, A is non-singular by a hypothesis. The number of rows is equal to the columns, and therefore the rank is full, so we have the rows is equal to the columns is equal to the rank, which means that if I take the reduced row echelon form of this guy, I'm going to have a pivot in every single row, in every single column, and therefore this reduced row echelon form has to be equal to the identity. Therefore, this E is also a left inverse, and by our previous theorem, these are actually equal to each other, remarkably. Therefore, we conclude A is invertible. That's really nice. That's really nice. So we have that this thing is invertible if and only if it's non-singular. If and only if it has full rank. Beautiful, right? So now this first trick, so the way we got X this matrix X suggests a way to compute the inverse of a matrix. So let's do an example for a 2x2 system. Right, so we've got A11, A12, A21, A22, and we're going to augment this with 1 in the first column and the zeros everywhere else, 0, 1, right? And in general, we would augment this with the identity matrix over here, and A would be any square matrix that we want to invert, or want to try to invert. And the whole thing is we're going to get this in reduced row echelon form, and we're going to see what happens over here, right? And this will be solutions, right? Over here we'll get solutions to x is equal to, ax is equal to this 1 sub 1, and this will be 1 sub 2 vector, right? And ultimately what we'll get over here is actually the inverse. This will be the x's that we want. Pretty neat. So let's do that. So the first thing is we multiply by 1 over A11, right? So our pivot is here as long as A11 is not equal to 0. If it were 0, then we could move this guy here, right? If it were 0, we could move this guy if this were non-zero. If they were both 0, then this entire thing would be a singular matrix. You can tell that it's going to be singular rather quickly, right? Because this guy, whatever, this has to be a 0 row eventually when you row reduce it. So without loss of generality, we can just assume that this is not 0, right? We're assuming that this guy is non-singular, of course. Otherwise, this will break down. So what do we get? The first step gives us 1, A12 over A11, 1 over A11, 0, A21, A22, 0, 1. The next thing we do is we subtract off A21 of row 1. So then we end up with 1, A12 over A11, 1 over A11, 0, 0 here. Over here we're going to get, if we compute it out, we get A11, A22 minus A12, A21 all over A11. We get minus A21 over A11 here, 1 there. So the next thing is, well, we want to turn this pivot into 1. So we're going to multiply this by, actually, A11 over A11, A22 minus A12, A21. And remember, we could only do this if this was non-zero. So what do we get? We get 1, A12 over A11. We'll get a 0, a 1, 1 over A11, 0. We get minus A2, 1, all over, so this will be a minus out here, A11, A22, minus A12, A21. We get A11 over here, A11, A22, minus A12, A21. Finally, we have to subtract off A12, A11 of row 2 from the first row. And what do we get? Well, we get the identity over here. And what we'll get here is actually going to be A22 over this interesting number, A11, A22 minus A12, A21. We'll get minus A12 over A11, A12 minus A12, A21. We're going to get minus A21 over A11, A22 minus A12, A21. And then here we get A11 over A11, A22 minus A12, A21. Whew! And this is going to be the inverse of the general matrix, and it's going to be well defined only when A11, A22 minus A12, A21 does not equal to 0. And we'll learn more about this when we talk about determinants.